This is Pre-Calculus A, Unit 4, Lesson 1, Polynomial Functions. So first we have to define what a polynomial is. Here's the definition. A polynomial function is any function of the form f of x equals ax to the n. I'll say a0 x to the n, or a1 x to the n, a2 x to the n minus 1, plus a3 x to the n minus 2, plus plus ax to the 1, plus ax to the 0, or just, So this is a sub n minus 1, and this is a sub n. Okay? Let me explain what that means. So it's made up of terms that are all added together. Each term has a coefficient, an x, and a power, or an exponent. And the exponents are integers. Not just integers, actually. They are positive whole numbers. Whole number exponent. Okay? So that's a class of functions called polynomial function. Poly meaning many, nomial meaning number or name, nomos. Okay, many names. So these are all examples of polynomial functions. Y equals x. Y equals 2x plus 3. Y equals x cubed minus 4x squared plus 7x minus 2. Okay, and we can talk about degrees. The degree of the polynomial, and notice I'm writing them in descending order of exponents. That's very important. Descending order of exponents. Exponent descending order. Highest exponent first, lowest exponent last, or constant term last. Okay? And that brings up another vocabulary word. This last term, that with no x, it's actually technically x to the 0, but it has no x because x to the 0 is 1, is called a constant. That's because it stays the same value regardless of what x is. Okay, write the exponents in descending order, and then you can find out the degree of the polynomial. So this is degree 1. This is degree 1, because the highest power on x is 1. This is degree 3. So a third degree or a third order. We'll also say third order polynomial function. Third degree or third order polynomial function. So that's a little bit of the vocabulary involved in polynomial functions. Okay, let's go to Desmos and let's play around with polynomial functions. Okay, the simplest polynomial functions is y equals a constant. And you'll notice it's a flat horizontal line. It has no curves. It has no slope, right? That's a zero order polynomial function. When I go to first order, y equals x plus 2, now we have a line that's got a tilt to it. Okay, it can be tilted up, tilted down. Whether it goes up or down depends on the initial sign on the x. Negative goes down, positive goes up. Negative goes down, not 0. Negative goes down, positive goes up. Now, much is made of something called end behavior of polynomial functions. Okay, the end behavior of y equals x plus 2, let's talk about end behavior. End behavior of y equals x plus 2 is it goes, as we go to the right, it goes up, and as we go to the left, it goes down to infinity. So as x goes to negative infinity, f of x, or y, goes to negative infinity. As x goes to positive infinity, as x goes off to the right, f of x goes off to positive infinity. It goes up indefinitely. Okay? Because it does this. It goes up as we go right. It goes down as we go left. Okay? That's its end behavior. Okay? Now let's look at that. We've got a 0-order polynomial and a 1st-order polynomial, both of them lines. 2nd-order polynomial, y equals x squared plus 2. Okay. So here we have a curve now. We have a curve, and it's got what's called a minimum value, right? A single minimum. We call this a global minimum. Global minimum, in that it is the lowest point on the entire function. That would be in opposition to a local minimum, which we'll get to later. But this is a global minimum. It has no global maximum. Notice the end behavior, if we look at y equals x squared plus 2, the end behavior is as we go to the left, as x goes to negative infinity, f of x, or y, goes off to positive infinity. As x goes to the right, to positive infinity, f of x goes to positive infinity as well. Okay, so it goes up on the left and up on the right. Okay, that's its end behavior. So that's a 2nd-order polynomial function, what we call a quadratic function. Okay, let's try a 3rd order. Y equals x cubed minus 3x plus 2. Okay. Now here we've got, you'll notice there are 2 bends, two curves, right? And there was one curve for a 2nd order. There were no curves for a 1st order or a 0 order. There was one curve for a 2nd order and 2 curves for a 3rd order. 2 curves for a 3rd order. And we can look at this. This is what we call a local maximum. It's a local maximum because it is the peak in this region, but if I go over here, the purple line actually gets higher than the maximum there. So it is not a global maximum, it is a local maximum. It also has a local minimum, right? Local minimum at 1, 0. So this is a 3rd-order polynomial function with 2 curves in it. One, what we call inflection point, where it switches from curving downward to curving upward. Okay, and its end behavior is this. So we've got y equals x cubed minus 3x plus 2, 3x plus 2. As x goes off to the right to positive infinity, it goes off to infinity. F of x goes off to infinity. It goes up to the right. As x goes off to the left, and I should have done this in the other order, f of x goes down to negative infinity. So it behaves like that. Okay? So that's its end behavior. Now hopefully you're starting to notice some patterns. Let's go to a 4th order. Y equals x to the 4th minus 5x cubed plus 3x squared minus 2x plus 1. Okay? This one, you got to zoom out a little bit to see it fairly well. It has 1 curve, 2 curves, 3 curves, right? 3 curves. Let's see if we can minus 8, no, plus 8. There we go. That's a little better curve for what I'm looking at here. It has 1, 2, 3 S-curves. Let's hide the rest here. Okay, it has 1, 2, 3 curves. Notice it's a 4th order polynomial. And it has a local maximum right here at 1.24, 8.364. And it has a local minimum here. This is not the global minimum because it's not the lowest point on the graph. It has a global minimum here. And it has end behavior that goes up to infinity as x goes to negative infinity, and goes up to infinity as x goes to positive infinity. Okay? And so we want to talk for a minute about how to tell the end behavior. First of all, a couple of things. The end behavior and the curves. All right? So here's kind of a rule. An nth order polynomial function has at most n minus 1 curves. Okay? An even order polynomial has matching end behavior. Let me explain what I mean by that. It's either up on the left and right together or down on the left and right together. They match. Up on the left and right together or down on the left and right together. An odd order polynomial function has disparate, not matching, end behavior. Either the left is down and the right is up, or the left is up and the right is down. Okay, and it becomes more obvious when I look at greatly simplified polynomial functions. Let's demonstrate. So y equals 1. Okay, that has no end behavior at all. It's asymptotic. So it's kind of, so y equals x to the 1, down on the left, up on the right. Y equals x to the 3rd, down on the left, up to the right. Y equals x to the 5th, down on the left, up on the right. Y equals x to the 7th, down on the left, up on the right. All that's happening is the curvature is getting more and more steep. In fact, if I do this, y equals x to the 1001, okay, it actually almost seems to turn a sharp corner. It looks square, right? It's not actually square. It is actually a smooth curve. If we zoomed in enough, we would see it. But it behaves down on the left, up on the right. So all odd degree functions, if the leading coefficient is odd, it'll be down on the left, up on the right, unless we make, and I'm going to treat the negative, the third order one, unless we have the leading coefficient negative, then things are reversed, up on the left, down on the right. Okay, look at x squared. Okay, up on the right, up on the left. Y equals x to the 4th. Up on the left, up on the right. Y equals x to the 6th. Up on the left, up on the right. Y equals x to the 8th. Up on the left, up on the right. And again, I can pull this here. Y equals x to the 1002. Again, it looks square, but it's still up on the left and up on the right. It's not actually square if I zoom in enough. Okay, but it behaves up on the left, up on the right. Now, going back to x squared, as our simple case, if I put a negative, if the leading term is negative, it's down on the left and down on the right. So knowing the degree of the polynomial function and knowing the sign of the leading coefficient tells you whether it's going to be up on the left, up on the right, down on the left, down on the right, up on the down on the left, up on the right, or up on the left, down on the right. Okay, and you can have fun, play with your graphing calculator and get a real good feel for it.